In this video, I'll be going through my notes on Level 3 wave systems. A link to the PDF and a list of corrections is in the video description. Wave motion. A wave is a propagating disturbance. They cause a relocation of energy, but not matter. Water and sound are mechanical waves, which require a medium or matter to travel through. Light, or electromagnetic waves, do not. We can furthermore classify waves as either transverse or longitudinal. Examples of transverse waves include water and light, and a transverse wave by definition oscillates at 90 degrees to its direction of travel. That is to say, if our wave is traveling in this direction here, the oscillations are going to be at 90 degrees to that. So in this direction here. We call the top of a wave the peak and the bottom of the wave the trough. Halfway in between is what we call equilibrium. The distance to which from a peak or a trough is what we call the amplitude. And the distance between two identical parts on the wave, such as a peak to peak, is what we call the wavelength, represented by the Greek letter lambda. An example of a longitudinal wave is sound. Longitudinal waves oscillate in the direction of travel. So if our wave is traveling in this direction, the oscillations are in that same direction. So we have compressions, which are our peaks, and expansions or rarefactions, which are our troughs. Once again, the distance between two identical parts of a wave is called the wavelength. We define the period as the amount of seconds per wave, or in other words, it is the time taken for a complete wave cycle. And specifically for moving waves, it is the time for a complete wavelength to pass a fixed point. So for example, say you are standing in shallow water at the beach. If when one wave passed you, you started your stopwatch and then stopped it when the next one hit, the time you would record would be the period. Frequency is the amount of waves per second. Specifically, it is the amount of wave cycles per second. And for moving waves, it is the amount of waves passing a fixed point per second. And so if you're once again standing at the beach in shallow water, and you found that half of a wave passed you per second, then your frequency would be 0.5. As our language might suggest, period and frequency are mathematical reciprocals, meaning that we can write the frequency is 1 over period, and the period is 1 over frequency. And now the unit of hertz is just another way of writing 1 over seconds. Wave speed. Wave speed can be written as velocity is distance over time, an equation that you're hopefully well familiar with. We can also define wave speed as the time taken, aka the period, for a complete wavelength to pass a fixed point. In this case, we replace our d with lambda, our wavelength, and our time with our period. And now substituting period is 1 over frequency, we can write this term here, which simplifies to wave speed is frequency times lambda, an equation that you're given on your formula sheet and you're going to become well familiar with. Let's use this in an example. Calculate the velocity of a sound wave with a 440 Hz frequency and 0.75 meter wavelength. We know that velocity is frequency times wavelength. We know both, which gives us 330 meters per second. Going through another example, calculate the wavelength of a 20 kHz radio wave. The speed of light is 3 times 10 to the 8 meters per second. Knowing that velocity is frequency times wavelength, we can rearrange for wavelength by dividing both sides by frequency, put in our numbers, which gives us 15,000 meters. Types of waves. In this course, we will be covering the following types of waves. Light waves, which travel at 3 times 10 to the 8 meters per second in a vacuum, and are transverse waves. Water waves, which are a traveling disturbance of the surface of water, and are also transverse waves. And lastly, sound waves, which travel at roughly 340 meters per second in air, though this depends on the temperature and altitude. It travels faster in denser materials. So for example, sound travels faster in water than it does air. It requires a medium to compress, and so sound cannot travel through space. And unlike our other two, sound is a longitudinal wave. Light. Light is an electromagnetic wave, which means it's made up of fluctuating magnetic and electric fields. And say if we had a photon of light coming out of the page towards us, it would have a magnetic field fluctuating in one direction and an electric field fluctuating perpendicular to that. This means that light not only has a direction of propagation, it also has an orientation. This property of light allows us to make a range of interesting things, such as polarized sunglasses, LCD displays, and 3D movies. How light behaves depends mainly on its wavelength. For this reason, we categorize light into 7 wavelength-dependent groups. The longest wavelength are radio waves, which are useful for things like radar and AM/FM radio. Microwaves are used for things like Wi-Fi, Bluetooth, and microwave ovens. Infrared waves are used for things like TV remotes. We of course have the spectrum of visible light, and then above violet we have ultraviolet, which can be used to cure resin and also sterilize medical instruments. We then have X-rays, which are useful in imaging, as they have enough energy to penetrate the human body and create a shadow of your skeleton. It's also useful for radiotherapy, which is a form of cancer treatment. And lastly, gamma rays have the shortest wavelength, highest frequency, and are useful in things like PET scans, which stands for positron emission tomography, which uses pairs of gamma rays to map the human body. Light travels at 300 million meters per second, or 3 times 10 to the 8 meters per second. Unlike sound, it does not require a medium to travel through, and so it can of course travel through space. Sound. Sound waves are propagating waves of compression and expansion. They require a medium to travel through, since they require something to compress and expand, and although it is a longitudinal wave, it is often represented as a transverse pressure wave. So if we had our wave with our compression, expansion, and so on, we can represent this as a series of peaks and troughs. The frequency, aka the pitch, is inversely proportional to wavelength. Therefore, as one increases, the other decreases. So if we had the same wave velocity, a large wavelength is going to mean a lower frequency, and a smaller wavelength is going to be a higher frequency. Sound tends to travel faster in denser materials. So for example, we typically see sound traveling at 340 meters per second in air, and typically around 1500 meters per second in water, and in the ballpark of 3000 in iron. Phase. Phase is a way of comparing different points in a wave cycle. And just to note, a complete wave cycle is 360 degrees, which we also write as 2 pi. And so if we're going to look at the phase difference on a single wave, defining points A, B, C, D, E, and F, the phase difference between A and B is 90 degrees. Since this whole length here is 360 degrees, and the difference between A and B is 1/4 of this, 1/4 of 360 degrees is 90 degrees. The difference between A and C is 180, since they are half a wavelength apart. A and D are 3/4 of a wavelength apart, and so their phase difference is 270 degrees. As with A and C, B and D are half a wavelength apart, and so their phase difference is 180 degrees. And if we look at B and F, if we start at B, we have one wavelength followed by another wavelength, which gives us 2 wavelengths, which is 2 times 360, which gives us 720. And lastly, if we're to look at C and E, these are both exactly 1 wavelength apart, and so their phase difference is 360. Looking at the phase difference between waves, waves are in phase when they line up perfectly. However, if we were to shift one of these waves a quarter of a wavelength forwards or backwards, then they would now be 90 degrees out of phase. Shifting one of the waves by half a wavelength makes the waves now 180 degrees out of phase, so that peaks line up with troughs and troughs line up with peaks. Superposition. When a wave occupies the same position as another wave, their amplitudes add together. And so if we have an amplitude of 1 and add on a wave of amplitude 2, the resulting amplitude is positive 3. However, if we had an amplitude of -1 and add on an amplitude of -2, the resulting amplitude is going to be -3. When waves combine and form a larger wave, as they have done here, we call this constructive interference. Now, if we had a wave of amplitude -1 and then added on a wave of positive 2 amplitude, -1 plus 2 is positive 1, and so our resulting wave has an amplitude of positive 1. And then if we have a wave of positive 1 amplitude and add it to a wave of -1, plus 1 minus 1 is 0, and so we have complete cancellation. When waves combine and form a smaller wave, or cancel out, we call this destructive interference. Standing waves. When identical waves traveling in opposite directions overlap, they produce stationary points of constructive and destructive interference. This can, for example, occur when a single wave is reflected back on itself. And so if we had some source, so perhaps a speaker, generating our orange wave, if we had some surface here reflecting waves, then this purple wave here might just be a reflection of the previous orange wave. Our pink regions represent what we call nodes, which are areas of destructive interference, where the peaks of one wave meet the troughs of another, which is to say they're 180 degrees out of phase, resulting in complete cancellation. Our blue areas represent what we call antinodes, which are areas of constructive interference, where peaks are meeting peaks and troughs are meeting troughs. That is to say that the waves are meeting in phase, resulting in a combined amplitude. And so in this diagram here, these regions represent areas where there is no movement, and in between we have the wave going up and down. So the solid wave and the dotted wave are just the same wave at different moments in time.
This here is a Tibetan singing bowl, though it goes by many other names. By dragging this leather-wrapped mallet around the outside, we can excite the bowl to create sound. Similar to a wave on a string, the bowl exhibits harmonics. Our first harmonic can be thought of as just a simple squeezing and stretching of the bowl. Here you can see there are 4 regions of the bowl that are moving in and out, corresponding to 4 antinodes. Now, while this motion is too quick and too subtle to notice with the eye, we can notice it with the ear. If you listen closely, every rotation of the wrapped leather will be accompanied by 4 increases in volume, corresponding to our 4 antinodes. What we're essentially doing is dragging this pattern around in a circle. As with a wave on a string, you can also get higher harmonics, such as this one here.
String harmonics. When a string is vibrated, multiple standing wave patterns are formed simultaneously atop each other. We call these patterns harmonics, each with a different wavelength and frequency. A string fixed at both ends has nodes at both. And so the first harmonic, which we also call the fundamental, since it's fixed at both ends, it has a node at both ends. And being the first harmonic, it is the simplest pattern we can get with a node at both ends, which is just the middle going up and down. And so we have nodes at both ends and an antinode in the middle. And now if the length of our string is L, then since going from node to antinode to node is half a wavelength, the wavelength of the wave that we see here must be twice the length. Another way to think of this is that we have both our nodes and our wave going up and down in between. To get a full wavelength, we just need to add another one of these. The frequency of this first harmonic, our fundamental, is denoted as F0. Our second harmonic, also called the first overtone, is one step more complicated, with nodes at each end, as well as one right in the middle, and now we have two antinodes. This here is a whole wavelength since it goes up and down and returns to where it started, and so our wavelength is just the length of the string. And the frequency of the second harmonic is 2 times the fundamental. The third harmonic, or second overtone, adds on one extra antinode. And if we were to divide this into thirds, we could see that a full wavelength is 2/3 the total length. And the frequency of the third harmonic is 3 times the fundamental. For the fourth harmonic, or third overtone, we add yet another antinode. And as you might see, a full wavelength is just half of our total length. So the wavelength is half L. And as you might have figured out the pattern by now, the frequency of our fourth harmonic is 4 times the fundamental. Theoretically, the amount of harmonics is infinite, though as the number of the harmonic increases, the amplitude of that harmonic decreases, such that of these 4 harmonics, the first harmonic is always going to be the loudest, and the fourth harmonic is going to be the quietest. Let's now go through an example. The waves on a 1.1 meter string travel at 410 meters per second. Calculate the frequency of the third harmonic. And so if we're going to draw the third harmonic, as you might recall, that looks like this, where we have 3 antinodes. Dividing this into thirds, we see that a full wavelength is 2/3 of our total length. And so we can write that the wavelength is 2/3 of our length. Putting in our 1.1 meters gives us 0.73 meters. And now to find the frequency, we can recall that the wave speed is frequency times wavelength. Solving that for frequency and putting our numbers in gives us 560 Hz.
The equipment here is set up to generate waves at a frequency shown on the display. The waves then travel down this length of elastic and reflect off the end, interfering with the original waves and producing a standing wave pattern. In this case, at our fundamental frequency of 4 Hz, we see the first harmonic. To get our higher harmonics, we just need to multiply our fundamental frequency of 4 Hz by whichever harmonic we're looking for. So for our second harmonic, that's 8 Hz. Third harmonic is 12 Hz. Fourth harmonic 16. Fifth harmonic 20. Sixth harmonic 24. Seventh harmonic 28. And eighth harmonic 32.
I have here an electric guitar. We can selectively silence harmonics by muting the string at a location where it requires movement. Any harmonic that generates a node at that location will be unaffected. When a string is played, all harmonics exist simultaneously layered atop each other. The lower the harmonic, the louder. Muting halfway silences the first harmonic. The loudest harmonic is now the second. Muting at a third of the length silences both the first and second. The loudest harmonic is now the third. Muting at a quarter of the length silences the first, second, and third. The loudest harmonic is now the fourth. We can also find the third and fourth harmonic by muting at the same distance from the other end of the string. Open pipe harmonics. An open pipe has antinodes at both ends, and so our first harmonic, aka our fundamental, looks something like this, where we have antinodes at each end and a node in the middle. And now to visualize our wavelength, you can see that we go from a peak down to a trough, and for a full wavelength, we need double this length to get us back up to a peak. That is to say that our wavelength is going to be twice our length, and once again the frequency of our fundamental is denoted as F0. The second harmonic, first overtone, adds in another node, and because it goes peak to peak, the length of our pipe is just a full wavelength, and the second harmonic is double the fundamental frequency. For the third harmonic, second overtone, we add in yet another node, and if we divide this into thirds, you can see that a full wavelength is 2/3 of the length, and the frequency is 3 times the fundamental. For the fourth harmonic, third overtone, we add in yet another node, and if we divide this length by 2, we can see that half of the length goes peak to peak, which is a full wavelength, so our wavelength is half L. And our frequency is 4 times the fundamental, and this continues all the way up to infinity. And note that although we are representing these patterns as transverse waves, they are in fact longitudinal, and so our representation looks transverse, but it's important to remember that the reality is longitudinal. That is to say, what we're seeing here is really a graph of the pressure waves, and there isn't actually anything going up and down. The direction of oscillation for a longitudinal wave is along this direction here. Let's now go through an example. The fundamental frequency of an open pipe is 2200 Hz. The speed of sound in air is 330 meters per second. Calculate the length of the pipe. And so to find the length of the pipe, we're going to need the wavelength. And since we have the frequency and the wave speed, we can use this equation here, dividing both sides by frequency to solve for our wavelength. Putting our numbers in gives us the wavelength of 0.15 meters. And now if we imagine our fundamental frequency, you might recall that it looks like this, and that the pipe length fits half a wavelength, where this is peak to trough, which is half a wavelength. And so the length of our pipe is half a wavelength. Putting that number in gives us 0.075 meters. Closed pipe harmonics. The opened end of a closed pipe is always an antinode. As waves travel down the pipe, they reflect off the closed end and experience a 180-degree phase change. That is to say, if we have the end of our pipe and we have a wave coming down like this, as it rebounds off the end, the wave is going to inverse, undergo a 180-degree phase change. As the incident and reflective wave are exactly out of phase at the closed end, a node is always formed there. And furthermore, only odd harmonics are possible in a closed pipe, for reasons that I'll go into in the next section of notes. And so our first harmonic, our fundamental, has a node at one end and an antinode at the other, and the simplest possible pattern in between. And now this here is a quarter of a wavelength. So if you imagine our wavelength as this here, what we're seeing here is just this section here, which is a quarter of the total wavelength. And so our wavelength is 4 times the length, and once again the fundamental is denoted as F0. And now our next harmonic is our third harmonic, first overtone, because only odd harmonics are possible, and so the second harmonic is not possible. The third harmonic introduces another node and antinode, and if we divide this pipe into thirds, we can see that we have 3 of our quarter wavelengths, meaning that a full wavelength we need to add on another quarter. Therefore, a full wavelength is going to be 4/3 of our length. And as per usual, the frequency of our third harmonic is 3 times the fundamental. For our fifth harmonic, second overtone, we once again add another node and antinode, and if we divide this pipe into fifths, we can see that a full wavelength is 4 of these fifths. So our wavelength is 4/5 L. And as per usual, the frequency is 5 times the fundamental. For our 7th harmonic, which is our 3rd overtone, we once again add another node and antinode, and if we divide this into sevenths, we can see that a full wavelength is 1, 2, 3, 4 of these sevenths. So our wavelength is 4/7 L, and the frequency is 7 times the fundamental. Let's now use this in an example. Calculate the frequency of the 5th harmonic in a 1.3 meter long closed pipe. The speed of sound in air is 330 meters per second. Considering our 5th harmonic, our full wavelength is this here, which is 4/5 of the pipe's length. And so we know the wavelength is 4/5 L. Putting in our L gives us 1.1 meters. And now to calculate the frequency, we can use V equals F lambda, rearrange for frequency, put in our numbers, which gives us 300 Hz.
This is a Ruben's tube. It consists of a metal pipe, closed at one end and with a speaker on the other. The pipe is filled with flammable gas, which exits through small holes in the top, and is ignited to display a standing wave pattern. The pattern in question is formed when the speaker produces longitudinal waves, which travel down the pipe, reflect off the end, and interfere with the original waves, creating nodes and antinodes. As I play a pure sine wave and increase the frequency, we can observe both that the wavelength decreases and that the pattern is more pronounced for specific frequencies. These frequencies, as should come as no surprise, occur at regular intervals since they are multiples of the fundamental frequency.
Why closed pipes don't form even harmonics. Recall that closed pipes require an antinode at its open end and a node at its closed end. And so the first harmonic starts with a node and then progresses to an antinode. Each additional harmonic adds on another one of these quarters. And so the second harmonic would start with our first harmonic and then add on another one of these quarter wavelengths, which would result in a node at both ends, breaking our initial condition here, and therefore the second harmonic is impossible. For the third harmonic, that adds on another one of our quarter wavelengths. So we have our first harmonic, our second harmonic, and then adding on another quarter we have our third, which puts a node at one end and an antinode at the other, and therefore this is possible. The fourth harmonic takes our third harmonic, and then adds on another quarter of a wavelength, putting a node at both ends, which is impossible. And lastly, our fifth harmonic takes our fourth harmonic, adds on a quarter of a wavelength, giving us a node at the closed end and an antinode at the open, which meets our initial condition and is therefore possible. And so for every even harmonic, you're going to have an antinode at the closed end, which based on this condition here, is not possible in a closed pipe. When asked to draw harmonics in an exam, the examiners will be strict on scale and drawing to the complete length. And so if you're drawing the fifth harmonic, you would draw it like this, which has the correct scale and is drawn to the complete length of the pipe, and so this is correct. However, if you don't draw this to the end of the pipe, it will typically be marked incorrect, and if the scale isn't consistent, it will likewise be marked incorrect. Here I have a tuning fork which resonates at a particular natural frequency. By placing a speaker nearby and matching it to this natural frequency, we can see it excites the tuning fork by observing the motion of the ping pong ball resting against it. Timbre. Notes played on musical instruments consist of all the frequencies of the excited harmonics superimposed. That is to say, when you pluck a guitar string, all of the harmonics possible are excited, and they all exist atop each other, or in other words, superimposed. The physical structure of an instrument affects how much each of these harmonic frequencies are emphasized. This gives every instrument a unique sound signature, which is called timbre. And so a tuning fork will tend to have a nice, clean sine wave, whereas each of these musical instruments would produce sounds of their own unique signature. One example of this that you might be familiar with is a graphics equalizer. A graphic equalizer is a tool used to change the timbre of audio. It changes the prominence of different frequencies without altering those frequencies. And so each of these sliders is increasing or decreasing a particular frequency range. For a deeper sounding tone, you might increase the lower frequencies and decrease the higher frequencies. Beating. When waves are observed from two sources at different frequencies, the waves alternate between in-phase and out-of-phase, and so we have out-of-phase, in-phase, out-of-phase, in-phase. This results in moments of high amplitude or constructive interference, and low amplitude destructive interference. We call these beats, and the resulting sound wave might look something like this, with high amplitudes and low amplitudes or cancellation in between. The frequency of these beats is the difference between the two constituent frequencies, and so the beat frequency is F1 minus F2, and these lines upon each side are a mathematical function that takes the absolute magnitude, which is to say it just makes anything inside of it positive rather than negative, so that if the result of F1 minus F2 was negative 5, these lines here would turn that into positive 5, and if it was instead positive 5, then it would remain positive 5. Let's now go through an example. A speaker playing a frequency of 100 Hz is positioned next to another speaker playing a frequency of 105 Hz. Calculate the beat frequency. So we have our two speakers playing their individual frequencies, and the frequency of our beat is just going to be the difference between these frequencies, which is 5 Hz.
Here we have two speakers playing separate frequencies, a microphone in the middle, plugged into an oscilloscope at the back. Currently one of the frequencies is much higher than the other, but as we drop it down, bringing the frequencies closer together, we start to observe a wavering. This is the effect that we call beats. The frequency of the beats is the difference between the two frequencies. These beats occur because the sound from the two speakers alternates between moments of constructive and destructive interference. As the frequencies almost match, our beat frequency slows and almost comes to a stop. As we continue to decrease our frequency, the beats once again speed up.
Diffraction. When waves move past a boundary, they bend around it. Larger wavelengths bend more than short. We call this behavior diffraction. And so if we had a barrier and we had long wavelengths which are approaching this barrier, then as they pass the barrier, they are going to curve around. Whereas if we had a shorter wavelength and the same barrier, we are still going to see curving around. However, because it's a short wavelength, we're going to have less curving. Or in other words, more diffraction for the longer wavelength and less diffraction for the shorter. Plane wavefronts passing through a gap diffract to form radial wavefronts. And so we essentially have the similar situation to before, except we essentially have a barrier on each side. And so we have plane wavefronts which pass through the gap and become circular. And we're going to see a higher amount of diffraction if we have a relatively small gap than we would for a relatively large gap. 2D interference patterns. When two wave sources are adjacent, they produce an interference pattern. The order number n is the wavelength path difference between the two sources. And so if we have our two wave sources, each producing regular wavefronts, right in the middle we have a line that represents 0 path difference, where along this line, waves are meeting perfectly in phase. Since the wavelength path difference is 0, we call this line n equals 0. As we move away from this line, the path difference between the waves increases either side, where on this side of our n equals 0, the waves from this source here are arriving slightly ahead of the waves from this source here, and the opposite is true for this side. Our green lines represent the antinodal lines, which are lines of constructive interference, where since the waves are meeting in phase, we have peaks meeting peaks and troughs meeting troughs. These amplitudes add to a new amplitude, and you'll note that our n number is a whole number, representing a whole number of wavelengths. Our blue lines in between are our nodal lines, which are lines of destructive interference, where the waves are meeting 180 degrees out of phase, such that the peaks are meeting troughs, causing the amplitudes to cancel out, giving us areas of 0 amplitude, and you'll note that our order number is something 0.5. So 0.5, 1.5, or 2.5, and so on. The 0.5s represent that the path difference is 0.5 of a wavelength out of phase. Path difference. Path difference is the difference in the distance between a selected point and each of the sources. It is usually expressed as a multiple of wavelength, for example 2 wavelengths, 7.2 wavelengths, or 3.5 wavelengths. Where the path difference is a whole number of wavelengths, there is an antinodal line. Where the path difference is something 0.5 wavelengths, there is a nodal line. So if we have our 2 wave sources denoted in pink and purple, each producing waves of the same wavelength, let's look at the path difference at 3 different points. For our yellow point over here, if we count the wavelengths from our purple source, we have 1, 2, 3, 4, 5, 6, 7. And from our pink source, we have 1, 2, 3, 4 and a half. 7 wavelengths minus 4.5 wavelengths gives us 2.5 wavelengths. Because the path difference is something 0.5, that means we have a nodal line. And we can furthermore see that because here we have the peak of a purple wave, and we're halfway in between the peaks of our pink wave, meaning that we're at a trough for the pink wave. Looking at our green point over here, we have 1 wavelength from our purple source and 1, 2, 3 wavelengths from our pink source. 1 minus 3 is 2 wavelengths, and because it's a whole number, it's along an antinodal line. Finally, for our last point over here, we count 1, 2, 3, 4, 5, 6, 7 wavelengths from the purple source, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 wavelengths from our pink source. 7 minus 10 gives us 3. Because we're taking the absolute magnitude, we make that positive, and so our path difference is 3 wavelengths. Because it's a whole number, that indicates that it's along an antinodal line. Diffraction formula. In this section, I'm going to go through a derivation that will allow us to put mathematics to the situation of 2-point interference. Knowing how to replicate this derivation isn't needed, however it adds some important context to the equations. So let's say we have 2 wave sources, a distance d apart, which is our slit spacing. Waves from each reach a point on a screen that is a distance L away. This test point, which is arbitrarily chosen, is a distance x from our central line here. Now because our wave source here is closer to our test point, the path travelled by our other source is going to be longer. This longer distance is indicated in green and is our path difference. This is found geometrically by drawing a line from our source here that intersects the path from our other source at a right angle. This gives us a right angled triangle where D is our hypotenuse, PD is our opposite, and we'll define our angle as being here. Using trigonometry on our small triangle, we can use the SO relationship which is that sine of the angle, is our opposite, which is the path difference, divided by the hypotenuse, which is d. Multiplying both sides by d gives us d sine theta is equal to the path difference. And now it's often useful to state the path difference as a multiple of the wavelength, specifically our wavelength multiplied by the order number n. This equation here is given to you on your formula sheet and applies in all of these situations. If we use the small angle approximation, however, we can derive another equation that, although it's simpler, it will only apply if this angle here is small. To derive this equation, we need to define a second larger triangle, which is this triangle here, where we have our angle theta, which, because geometry, is the exact same as this angle here. Our opposite is our x, and our adjacent is our L. And so for small angles, specifically angles that are less than 10 degrees, we can make this small angle approximation. This assumes that the antinodal lines intersect the screen at even intervals. So if we have our antinodal lines originating from our sources at small angles, you can see that they're roughly the same, whereas for larger angles, this approximation is less and less reasonable. Mathematically, the small angle approximation assumes that sine of the angle is roughly equal to tan of the angle. And so from the large triangle, we can use the TOA relationship, which is that tan of the angle is equal to our opposite, which you might recall was our x, divided by our adjacent, which you might recall was our L. So we can take this equation and replace our tan theta with our sine theta using our small angle approximation. And now if we replace the sine theta with x over L in our n lambda equals d sine theta relationship, so we're taking our equation from the last page, and because sine of the angle is equal to x over L, we're going to replace our sine of the angle with our x over L. If we do that and rearrange, we get dx over L is equal to n lambda. Now, just to recap, this is a handy equation because it's a little bit simpler than our n lambda equals d sine theta. However, it can only be used if the angles are less than 10 degrees. A common trap in the exam is to present a situation where this is not the case and penalize students for using this equation instead of this equation.
I have here a diffraction grating with 100, 300 and 600 lines per millimeter windows, and a column of LEDs of different colors. Viewing these through our grating, we can see that the higher the lines per millimeter, the greater the angles are between our orders.
Multiple slit interference. Until now, we've only considered two slit interference. The case of multiple slits behaves much the same, with several key distinctions. And so a pattern from a double slit would look something like this, whereas for multiple slits, which could be in the realms of hundreds or thousands, our pattern would look more like this. And so we have narrower lines because more sources are interfering, causing more destructive interference. Another way of putting this is that because you have more sources, there are more combinations of them that result in destructive interference. Furthermore, our points are brighter because more sources contribute to points of constructive interference. So for example, for a double slit, we would only have two sources letting in light to form this here, whereas for our multiple slit, each additional source means more light. So we only have two sources contributing to our peaks here, whereas we have more sources contributing to our peaks here. More sources, more light. One example of multiple slit interference is when using a diffraction grating, which are a film with thousands of lines, where each gap behaves like a slit. They are typically rated in lines per meter, where we can relate this to the slit spacing, as the slit spacing is 1 over the lines per meter. When white light is viewed through a diffraction grating, longer wavelengths appear at a larger angle than smaller wavelengths. So we have our central antinodal line, which is colored white because all the colors experience an antinodal line here. Whereas as we increase our order number, we see that the colors are spread out. with red occurring on the outside and blue occurring on the inside. This occurs because longer wavelengths have a larger path difference, not because they diffract more. This point is very important to emphasize because there are still some teachers that teach this, and not only is it completely incorrect, it will, as it should, award you no marks in the exam. And so to recap our actual explanation, when we have a larger wavelength, that means that our path difference n lambda must be larger, and since n lambda is d sine theta, if n lambda is larger then d sine theta is larger, and if d is constant, which it almost always is, then our angle must increase, as we see it does here. Let's go through an example. A 520 nanometer wavelength laser is shone through a 100,000 line per meter diffraction grating onto a screen 0.35 meters away. Calculate the distance between the central and third bright spot. And so we know our wavelength is 520, where a nanometer is times 10 to the minus 9 meters. We have our n, which is 100,000 lines per meter, and we have our order number, which is 3. Now our lines per meter isn't much use, so we need to convert that to our slit spacing. Slit spacing is 1 over our n. Putting that number in gives us 0.00001 meters. And now recalling n lambda equals d sine theta, where because we're wanting to find the distance, where our distance is our x and we know our L, we're going to want to know our angle. So we can solve that for our angle by first dividing both sides by d, and then taking the inverse sine of both sides. Putting our numbers in gives us 9.0 degrees. And now taking our right-angled triangle here and using the TOA relationship, which is that tan of our angle, is equal to the opposite x divided by the adjacent L, multiplying both sides by L to solve for the x. Putting our numbers in gives us 0.055 meters. Here I have a diffraction grating with 100, 300 and 600 lines per millimeter windows. Turning off the lights and firing up the smoke machine, we can see the interference pattern from this green laser. We can see that the more lines per millimeter, the greater the angle between our antinodal lines. I have here a green laser producing a beam with a wavelength of 532 nanometers, projecting onto a curved screen through a selection of 100, 300, and 600 lines per millimeter diffraction gratings. Let's predict the maximum order number for each grating. To do this, we use d sine theta equals n lambda, the maximum angle is 90 degrees, and sine of 90 is 1. So the equation simplifies to d equals n lambda, which solved for our order number is d over lambda. Our d is 1 over the lines per millimeter. Putting these numbers in, and truncating the result, gives us maximum order numbers of 18, 6, and 3, which when doing this practically, is exactly what we find. Secondary maxima. Consider a 3-source interference pattern. Maxima, which are our antinodal lines, occur when all 3 sources meet in phase, which is what we see here. With 3 sources, however, we also have regions where 2 out of 3 sources meet in phase. These regions form what we call secondary maxima. The more sources, the more secondary maxima produced. So if instead of 3 sources we had 4, then we'd have, instead of 1 secondary maxima, we would have 2. I have here a green laser projecting a dot onto a screen, interrupting the beam with a double slit. Each slit now behaves like a separate wave source. This creates an interference pattern with antinodal lines where the sources meet in phase, resulting in lines of brightness, and nodal lines where the sources meet 180 degrees out of phase, resulting in lines of darkness. Let's now replace the double slit with a triple slit. Now, in addition to the primary maxima, we now see smaller secondary maxima in between. As before, the primary maxima are where all sources meet in phase. In this case, there are now 3. However, at the secondary maxima, we now have points where only 2 of the 3 sources meet in phase, resulting in points of 1/3 the brightness of the primary maxima. With each additional source, we have an additional secondary maxima. We also see the pattern get brighter, as more sources means more light, and the primary maxima get thinner and sharper, as more sources means more destructive interference between the primary maxima, as there are now more combinations to achieve this. The Doppler effect. Moving wave sources produce wavefronts that are closer to the previous wavefront ahead and further from the previous wavefronts behind. So if we have our moving source producing wavefronts, ahead of our source we have a decreased wavelength, where we use lambda prime to distinguish it from the natural wavelength unaffected by the Doppler effect. So essentially it is the observed wavelength. Behind the source we have an increased wavelength, and because our velocity of the wave stays the same, that means that we have an increased frequency ahead and a decreased frequency behind. For observers perpendicular to the velocity of the source, the wavelength and frequency are going to be equal to the true ones, and so in other words, they will not experience the Doppler effect. And now looking at the relative wave source velocity. So for example, the relative velocity between a wavefront and the source. Because the source is moving away from the wavefront, this relative velocity is the velocity of the wave in this direction, plus the velocity of the source. However, for a wavefront ahead of the wave, because these velocities are in the same direction, these velocities subtract. If you're finding this at all confusing, then this would be a good time to revisit relative velocity from level 2 mechanics. And so the relative wave source velocity can be written as Vw plus or minus Vs, where the plus or minus is a minus for ahead and a plus for behind. We can therefore write this equation here, which I'm not going to go into the derivation for because you don't need to know it. The observed frequency f prime is equal to the true frequency multiplied by the wave speed, divided by the wave speed plus or minus the source speed, where once again the plus or minus is a minus for ahead of the source and a positive for behind the source. Let's go through an example. A car traveling at 30 meters per second approaches a stationary observer while tooting its 1200 Hz horn. Calculate the frequency heard by the observer. The speed of sound in air is 330 meters per second. So we have our car approaching our observer. We know the velocity of the car is 30 meters per second, the wave speed is 330 meters per second, and the frequency is 1200 Hz. Using our Doppler effect equation, where because our observer is ahead of the source, our plus or minus is a minus. Putting in those numbers gives us 1320 Hz. This is an applet designed to show how the velocity of a wave source affects the distribution of its wavefronts. For a stationary source, the wavefronts are uniform and equally distant. For a moving source, wavefronts are generated closer to the previous wavefront ahead and further from the wavefronts behind. When the source velocity approaches the wave velocity, the wavefronts stack atop each other, constructively interfering to produce a very large amplitude, which is observed as a sonic boom. Doppler graphs. If we were to graph the frequency against time for an object emitting a noise and passing an observer, we're going to go from a higher frequency as the source approaches, which is then going to drop down to a lower frequency as it moves away. Note that the true frequency is not halfway between. This might seem counterintuitive, like this is breaking some sort of symmetry. What I'm now going to do is try to explain why this is the case. Understanding the why is more of a scholarship physics level. However, for level 3 physics, it's sufficient just to know that the true frequency is not halfway between. It's fairly common in exams for them to try and trip you up on this. The reason for this asymmetry is that the observed frequency scales with the proportional difference in wave source speed and not the absolute difference. What I mean by that is if we have our toward and away situations, let's look at the absolute difference in speed. Consider the case where Vs is 10 and Vw is 20. When our source is moving towards, our relative wave source speed is Vw minus Vs. Recall that it's a minus because we're going towards. That gives us 20 minus 10, which is 10 less than our 20 Vw. For our source moving away, we instead add our Vs, which gives us 20 plus 10, giving us 30, which is 10 more than Vw. This apparent symmetry is why you might intuitively expect the true frequency to be halfway in between, because the absolute difference is the same. However, as noted, the observed frequency scales with the proportional difference in wave source speed and not the absolute difference. So what do I mean by the proportional difference? Consider our Doppler effect equation here. What I mean is that our frequency doesn't just scale by the absolute difference, it scales by this difference proportional to Vw, which for the case of the source moving towards is equal to 2. What this means is that our Vw of 20 is double our wave source velocity of 10. However, for our situation of traveling away, we get 2/3, and so our Vw of 20 is 2/3 the wave source velocity of 30. And so because the proportional difference is different, and it's the proportional difference that scales our observed frequency, the situation isn't symmetrical. I know this was a lot, and I'll reiterate that this explanation is scholarship physics level, and that for level 3 physics, you just need to know this statement.